Good morning to the two viewers that are on there, or whatever time it is in your part of the world. We're going to let a few more people join on, and Ian and I'll get started here. All right, good morning from our part of the world and whatever time it is where you're at. Thanks for joining us. I'm Dan, or Viking, and I've got Ian with me here. We wanted to talk through a couple of the binary challenges with you. First, I'd like to say some of the stats we've got on our CTF so far. A lot more than we were expecting. So we've got 204 teams registered at this point with 8,647 wrong keys. We got 1,684 correct keys submitted. And at this point, we've got a total of 35 challenges. We do have 4 more challenges that will drop after we're done here, give you guys something to work on the rest of the day for those that have completed this. Right now, our most solved challenge is Encoding Apprenticed with 114 solved. And our least solved is our Crypto 500 challenge that we just put up last night. If you ended up staying up all night banging your head, you can thank State Farm for that one. So we're based in Idaho, or most of us are, Utah. We're kind of amazed. We had over 40 countries on our scoreboard night before last when we checked. So hello to the international crowd. So these things do cost money. So I'd like to take a second to thank our sponsors who enabled us to do this. So big thanks to the Facebook security team and the Uber engineering security team, which have been working with us since a little before DEF CON on just getting us ready, as well as providing money for server costs and swag and stickers that I'm going to be sending out to people. Also, a big thanks to Snowfensive, who stepped up at the last minute and dropped money on us so we can send out some nice prizes to the middle school teams that placed. On that note, we weren't filtering, and we have no idea out of those 200 teams at this point who's middle school and who's not. So it'll take us a little bit. We'll be reaching out. We're a small team, and we're reaching out via email and trying to verify people over the next week or two. We're trying to be conscious of your privacy with your emails, so it's just a couple of us doing that. So be patient with us afterwards as we work through that. Last, I'd like to say big thanks to all of our DJs who just rocked it last night. State Farm, who started it and organized the whole thing. Metacortex, InfoSec Barbie, Skittish and Buzz, and last but not least, Whitey Cracker. All right, so I've got Ian on here with me. Ian, you want to say hello?
Hello.
All right. So we're having a tiny bit of trouble hearing each other, but we're just going to roll with it. So Ian, let's talk about the binary challenges. We reached far on this one, and we want to make sure that people at least got something out of it. So let's start maybe with some of the foundational pieces that one would need to understand to even approach these. If you don't mind, can you share the code from this is the end while we talk here, so they have some code to look at?
Absolutely.
I'm going to make you the presenter. Okay, that's me.
All right, can you see my screen?
Yep, got it. All right, we got code. Excellent. So we'll just leave that up in the background while we kind of talk through what you need to understand to exploit this program.
All right.
Yeah, go ahead, Ian.
All right. Well, just let's look at the code first off and see what's obvious here, right? We can see that there's a flag here, and that's probably the first thing that everybody saw. You're probably programmed to see that format at this point in the CTF. And then we're also asking questions here. You know, what's your name? And then we're accepting that input, which is what this scanf does. And then we're writing that back out. So it's pretty basic what's going on. There's a string copy here in between on line 15 that I'll talk about here in a second. But really, is what we're doing here is this is a single function. We don't have any global variables in that. And what that means is there's nothing that's stored. Everything that's stored that we're interacting with in this program for this particular purpose is all in local scope. And is what that means, at least on an x86 processor, is it's stored in the stack. So, and
Ian?
Yes, sir.
Let me cut in for a second. You're talking about x86 architecture. So is that's something that everybody uses? What do you mean by the architecture?
Sure. Yeah, x86 architecture is your most common architecture that you're going to use for like your laptop, your PC, even Macintosh uses the x86 architecture now, and it's really just it's a chip design, AMD and Intel chips that everybody's familiar with, that they play their games on and that they do their schoolwork on. Those are x86 systems. That's different from what like your phone has in it, which are generally ARM-based architectures, which is it's just a processor layout, and it defines specifications on how they work, really, is what it comes down to.
So you mentioned stack right before I jumped in on you. Is that different across these two architectures?
It absolutely is.
Okay.
The stack is used for storing local variables. These two lines right here, 8 and 9, are pointing to spaces in the stack. And the stack is something that's kind of used to just set information down, and then you can come pick it back up, right? And it's called a stack because we just stack things on top of each other. Now, in the x86 world, that stack has a property where it grows from a high number and it gets smaller. So if we're storing stuff in slot number 10 on the stack, then the next slot that we have available is slot number 9, and then 8, and then 7, and so on. So as we pull stuff off of it, we'll go back to 8, 9, and 10 as we pull things off. And that's different from other architectures. ARM, depending on the way you have it set up, will grow down, but oftentimes it'll grow up. It depends on which way you have it set up.
And you mentioned, so it's going from like high memory addresses to low memory addresses. Maybe you're going to get to this, but when you write to the variables, is it also going from high memory to low memory? And does that affect this whole problem here at all?
Yeah, that's an interesting side effect, actually, the way that the stack growth works. And, in retrospect, I wish I had a visual for this, but whenever we write into computer memory, it's moving forward. So if I have a name to store, like world, is what we're going to do is it's pointing to a specific spot in memory. This buffer is pointing to a specific spot in the stack. So say we're looking at slot number 10, and I put in the letter W, will go into that slot number 10. And then the O next will actually go into slot number 11, and so on. So the word I'm putting in will grow further into memory. It'll grow to higher values as I put data in. But as I use the stack, it grows towards lower values. And you can see how that could be a problem, because I can overwrite data if the program didn't take care to protect itself from this. I could overwrite data that is in previously used stack addresses.
So let me repeat that back, make sure I understand you. As we're adding things to the stack on x86 architecture, starting at high memory and then working itself to lower memory. But then as we write back to those variables, it's growing back up towards the high memory. Is that correct?
That's correct.
Okay. And maybe we should have gone back on this. The stack, is this something that's common to like all architectures? Is this a CPU thing? Just a made up data structure for computer science, or?
Yeah, so this is specific to the architecture. This is a decision that was made by the engineers who built the chip. And stack growth direction is it growing down is actually pretty common. It's common certainly in the concept that the Intel 86 architecture is common, but it's also common in other architectures. I do believe that ARM thumb mode, for example, grows down as well. And there's a whole great deal of many other architectures that also grow down, but they don't all grow down. So this is something that you would need to, read the manual on your processor, and that'll give you the most information about it.
So I just like to add to that. We're really just scratching the surface, if you're not catching that already, of what can be done here. But we wanted to really provide here with some sort of introduction. We got some links to some playlists that I'll tweet out afterwards if you want to go learn more. So we are going to take some wide strokes on this. Okay, let you go back, Ian. Thank you.
All right. Well, why don't we run this program and see what it does here? Oops. Okay, so when we run this program, it's asking, what is our name? I'm going to rearrange my windows here slightly so we can see the code. Okay, so on execution, the first thing we see here is, what is your name? And that's this printf statement, and it's asking us for us to presumably type in our name. I'm going to type in world. And as soon as I hit enter here, this world variable is pulled into buffer, which this buffer is just a pointer to this stack location. And this stack location has a size to it. It'll hold a certain amount of data. After we do that, then I copy the flag into memory. I'll go over that in a second. And then we print the message back out, hello, whatever they typed into buffer. So we can store pretty big values in here. It's quite a bit of space for us to do that. And see, nothing's really happening here. You got hello, very long list of A's. But there are some limitations. And specifically with this method that I'm using, strcopy, it doesn't really care, scanf, it doesn't really care what the length of that buffer is. So if we come up here toward the top, I have a buffer size of 4096. That means that I can put 496 characters to. So how do I get 496 characters into this buffer? Like, this is a hard thing to do, right? I don't want to write that many letter A's on my command line. So what I can do then is I can actually use another program to do this for me. Use Python to execute a task.
Ian, is there anything that we're not seeing there that's going into that variable? I see all the A's there. But the name of the challenge is this is the end. Is there anything that we're not seeing that's going in there as well?
Yeah, I guess I should touch on the string copy at this point. So if we look at where buffer is, it is identified below the flag variable. And because of the way that was organized, the buffer variable is pointing to a later point in the stack. So it's pointing to a lower memory address. So as we write data into buffer, it gets closer and closer and closer to where the flag variable is stored, at least where that pointer is pointing to. Now, immediately after we accept the user's input and we stick it into the buffer, we then copy the string constant flag into the flag location in the stack. So, and if you guys can't see that here, let me full screen this. Flag is a string variable, a string constant that we're just basically, it's identified in a place in memory that's read-only, and we are moving that from this read-only place in memory into our local scope in the stack pointed to by the flag variable. And that happens to occur just after the space we have reserved for, just before the space we have reserved for our buffer. And I say before in the sense of the stack location, but in terms of memory location, it comes after the place we have available for storing our buffer. Does that answer your question?
I lost a tiny bit of audio near the end. What I was getting at was like how it terminates strings. Did you cover that?
Actually, no, I haven't. So when we write a string into memory, if I put in world here, if that was what was being sent into this buffer, what that would do then is up here we might see something like this, and this terminator here at the end, this 0. This is a special way to put it, and actually, let me write this a different way here. So what goes into memory when I type the string world is, of course, world, as you might expect. Each character is stored as its integer representation, and it gets all the way to the end of that, and then it puts in this special character, which is in this case 0. But that means something special in the string library in C. And what that is it means that this is the end. It's the end of the string. You can't read past this point. And because that null terminator gets stuck in there, that will effectively end the output, that when we print whatever that buffer content is, it will stop as soon as it hits the 0, right after the letter D there.
So the print doesn't actually care that where the end of your variable actually lies according to the size. It just looks for that 0. Is that what I'm hearing?
That's absolutely right. Yeah, the buffer size of 4096 means nothing. It's all about that 0 terminator.
And then I was wondering this since this morning. Does that 0 terminator count against the size of your buffer?
Yeah, actually it does.
Okay.
Yes, it does. So immediately after we put that input into buffer here, then the string copy occurs. So if we logically think about what's going on here, let me draw a little bit more ASCII art here, and hopefully this will help us see what's going on. All right. So if right at this location in memory is the buffer, and all the way over here at some point is where we're storing flag. Oops, let me correct my variable. All right, somewhere way over here is where we're storing flag, and what does that look like? It's like flag. Anyways, you get the point. If I continue to write data here, so if I continue to write A's, then I can get into that space and then print out whatever's left. And I'd kind of like to demonstrate that here.
So it's going to print out until it hits the null terminator from the other variable at that point?
That's correct. At some point we'll get to the end of flag and we'll have 0x00, and this will be, the flag data.
Okay.
And this is possible because of the string copy here. We're putting the string copy in and we're overriding our buffer's null terminator. That's why this is happening where it's happening.
So friends don't let friends use string copy?
Yes, absolutely. All right, let's go ahead and we ready to run this and see what it does? So I need to input data here, and I'm going to use a different program to do this. And actually, just to describe what I'm doing here, Python is an interpreted language. I hope y'all are familiar with. I'm just using it to print out a string for me, and this is useful because I can do math on a string. So like I can print 10 A's or 1,000 A's, or what I really want to do is 496 A's. So now I'm going to use that. I'm going to pipe that through this program, and we'll see what happens here. You see here, all the way at the end of this string is a flag that popped out. Now, just to prove that that number is what's important, I'm actually going to do this with 495 strings, letter A's, excuse me, and you'll notice it didn't work. So you got to get past that null terminator there right at the end, and make sure that it gets overwritten when the string copy puts its data into the flag. You have any other things you wanted to look at this one on, Dan?
No. If any of our viewers on there from Slack, you can drop a question and we'll try to get an answer if there's something we glossed over that you'd like to hear. For the new viewers that hopped on, when we're done at some point, we'll come back through this and try to make this live so you can catch the first part of it. So I'm just going to summarize what I've heard, Ian. You've got the variables going on to the stack from high memory addresses to low memory addresses. As you write to those variables, it climbs back up the stack. The variables are terminated with the 0 or null terminator. So if we can overwrite that, printf doesn't actually know where the end of the variable is, and it'll just keep searching for a null terminator. Does that sound right?
That's it.
Okay. So briefly, because it's not really our target audience, could this be much, much worse?
Oh, absolutely. It all depends on what's in that memory. In this place, well, think of it in this case, actually. What's in that memory right now is the flag, the one thing that we're trying to hide, right? And it got leaked out because of poor programming strategy. What else could be stored in memory? Well, there's everything stored in memory. SSL private keys. This is a very similar thing that happened with the Heartbleed virus, or Heartbleed wasn't really a virus. And many other security issues can come up in software. This is a big one. So much so that there's actually safeguards in place to protect programmers from doing this, which we had to disable to get this challenge to work.
Okay, thanks. Yeah, and we'll drop some video playlists if you want to go further and read about that. You're saying everything's on there, so as you learn more about the stack and like as you jump into functions, stack frames and return addresses, and we have unchecked buffer overflows on our server for those that know. So have fun. We'd like a write-up if you own our server. I think that's pretty good for that one. I don't see anybody. Oh, no, I don't see anybody on Slack asking questions. So want to move on to the format my world, please?
Yeah. We get set up here. All right, format my world, and I'm going to close this just because it's here we go. Okay, so format my world is a very similar C application. You can see it's kind of got the same layout here. We got buffer at the top, we got the flag, and then there's this format here, and then buffer immediately following that. Once again, asking a question, accepting user input, and then we're printing back out the response. This one is interesting because you'll notice I'm not moving memory around after I take user input. What's going on here is a lot more subtle. So taking what we know already about the stack and the location that buffer is sitting in as relation to the format variable, you can think what might happen here. So and let's go through this logically. If I put in blue as asking my favorite color, then that is going to get stored into this address, right? So let's I'm gonna draw this slightly differently this time. So I'm gonna put in the letter or the color blue. And at some point, our null terminator. So if I just did this, and of course there is, 496 bytes of data in between here and there. But if I just did this, then I would end up just printing out the letter E. And we can try this real quick.
And after you show that, Ian, I didn't hear, did you talk about format strings?
I have not talked about format.
Okay. Show them and then maybe back up and tell us what format strings are, if you would.
Yeah, absolutely.
Okay.
Oops. Lowercase c. Oh. Okay, so let's go just a little further here and go 497. That's interesting behavior, right? That's not doing what we saw in the previous one. And the reason is because we're printing format, and format is pointing at this case at the letter A. So that right there, that line on line 10 as it's described, is what's being printed out to the screen here. Well, printf, and if we look at printf, there are details about passing parameters in and how to display those on the screen. So if we run this without any arguments, let's type in a letter blue, we get a that's cool. By the way, the flag is located in memory at this memory address. That happens to be the location in global memory space where the string constant is stored. So as you can see right here, all the way toward the end, line 15, there's this %p, and I'm looking at line 15. And as what that has is, it's telling the printf function to interpret the variable that's handed into the printf function, in this case, flag, interpret that as a reference in memory and show the address at which that memory points to, or that memory that we're describing. So there's other formats that we can pass into the printf function. For example, if we wanted to print a, actually, I believe we saw this in the other code here. We were printing a string, as you can see right here. So in the end challenge, we were using the string format to present whatever the user's name was that they typed into the buffer.
So we had a format string in the first one as well. It just wasn't vulnerable. Is that correct?
Yeah, that's exactly correct.
And when you put that together, was that a hint for the next one? Like, hey, here's another way to do. Is that what you were thinking, or is it just a coincidence?
Well, it was more of a coincidence. I mean, I'd like to think that without seeing the code, I think it would have been difficult to analyze that. So.
And we did end up sharing the code on those challenges. For,
oh, that's right.
Right.
That's right. then we'll say, yeah, that was absolutely intentional. So, all right, if we change this, and we can do this right now. In fact, I'm going to alter this program. Let's see here. Did I mess anything up now? I'm going to alter this program and recompile it just so you guys can see. And just running it as unabated here, you can see that the %s is printing out the actual string, the content of the memory of the data located in memory pointed to by flag. So all I need to do to take advantage of this this application is get a %s into the format. And based off of the previous challenge that we had, we actually know how to do that. So if I am writing a sequence of numbers that overrun the size of the buffer, I start writing into format. So all I need to do is get this particular character to be a %s, and then I'll have the system print flag out for me. So let's give this a try. And yes, there we go. So just to prove that worked, if I can actually put other data in here. See if that, yeah, there we go. So we had an extra, I have an extra A character in there left over from the.
So what I'm seeing here, it looks like if you get the %s anywhere and after the first null terminator into the second variable and anywhere in there before the null terminator, you're good?
That's correct.
Okay. Cool.
Yeah, we're basically rewriting this format to whatever we want it to be. In this case, that last one looked something like this. And it works just as you would expect it to if I compiled it and ran it that way. So, got anything else we want to consider about this?
Anybody on here from Slack, you can drop a question in there. We'll answer. I can't think of anything else, but I can't really think after not sleeping all weekend either. So I think you've done a pretty good job of covering this. Thanks so much for putting these challenges together and taking the time out of your morning to share with us, Ian.
Oh, absolutely. And
was there anything you wanted to add before I wrap this up?
Absolutely. This is just scratching the surface, right? Like, this is kind of fundamental knowledge that you would want to be aware of. And to be honest, these security vulnerabilities that we're showing are, for the most part, they're taken care of. But the way that they were taken care of is not something that the developer is necessarily aware of most of the time. So other flaws in the system can reintroduce problems like this. And the reason I want to say this is because although this seems overly simplified and it seems like this would never happen in the real world, it can, because most people don't think about problems like this and they assume they're taken care of for them. So we all, as software engineers, as computer scientists, or as people trying to protect systems that we're responsible for, we need to be aware of these types of problems. Even if they're solved at the moment, they're still important to understand because they can be reintroduced, and it's happened in the past and it will happen again. But more for now, this is just fun stuff, and I suggest you read more about your processor, because that's where all this stuff's happening at.
Okay, well, yeah, thanks again. So for those of you guys who tuned in, I promised a hint for the Connect 4, which we don't have very many people solved it. That was Neo's baby, and he said, just read what it tells you to do. Before you even connect to the Connect 4, go back to the problem and read the first thing that it says. Don't overthink it. Just do what it says. It's much simpler. You don't have to program or anything to beat that one. Last, I'd like to thank our sponsors again. Facebook security team, the Uber engineering security team, and Snowfensive for enabling us to put this on. None of it's free, so we're a small team. It's nice to not have to pay for it out of our pocket. Last, if you like this, come give us some feedback. We're talking about, we're doing some walkthroughs on the rest of them. Probably not today, but in the future after we've closed things up. So thanks for joining us, everybody. And we're going to go make some more challenges live so you guys have something to hack on. We'll tweet out a close time, but it's sometime this evening. We're in UTC -7, so Mountain Time Zone for the Americans. Thanks, everybody. Thanks, Ian.